Well, has the Big Bang Theory been disproven? That's a little bit of probably not the best language to use, but their claims are now that the images from the James Webb Telescope, the space telescope that's bringing back these new images, is actually disproving current models on the Big Bang Theory. We're going to dive into that. I'm Pastor Josh Barnes. Thanks for joining us here on Point of View. This is the show where we're unashamed to look at political, social, cultural, and theological issues, all from a biblical worldview. We do that because the Bible's true. We know that for a lot of reasons, but probably the biggest reason is because Jesus actually died and actually rose from the dead. And if the Bible's true, and we know that it is, then we can't be right about any issue if we disagree with the Bible. So that's the premise of the show. Yeah, I've read just recently came across an article from a man, Barry Setterfield, who works in creation science and that kind of thing. And his claim was that these new images, that you've probably seen them online, these new images from the James Webb Space Telescope actually disproves the Big Bang model, because apparently, I'm going to try to give you a layman's explanation. Apparently, there is a way that they measure how old these galaxies are, which I guess makes sense because we're seeing light from a long time ago. And when they're looking so far back, they're expecting that about 1 billion years after the Big Bang, that there's going to be no galaxies or anything in that age range. But they're finding galaxies as far back as 200 million years after the Big Bang, and they're huge. They're just more numerous and more stars in them, and all of these problems apparently for the current models. But I am about as far as you can get from an astronomer. So I turned to our good friends at Answers in Genesis and asked if we could have someone come on and actually explain if this is correct and exactly how does this work, explain it to us, and we have the absolute best. I'm joined now by Dr. Danny R. Faulkner, and Dr. Faulkner has a PhD in astronomy. He also has degrees in physics, and I think probably a couple other things. Dr. Faulkner, thank you so much for joining us on Point of View today.
Oh, you're very welcome. It's a pleasure to be here with you.
Yeah. Okay. So you're at the Answers in Genesis offices right now?
Mm-hmm.
All right. This is live, or not live, but recording straight from Answers in Genesis. Here we go.
Yes.
By the way, just before we get started, love the ministry out there. We really appreciate all the work you guys do in diving into these. Give us maybe a summary of what your thoughts are on this, on the James Webb Space Telescope, and what the findings are.
I think I need to back up and talk a little bit about the telescope itself. It's been called the replacement for the Hubble telescope, but in many respects it isn't. It's kind of it goes beyond it in a different way. The Hubble Space Telescope was dedicated to what we call the optical part of the spectrum, what we see with our eyes, and a little bit in the ultraviolet, and a little bit in the infrared. The James Webb Space Telescope doesn't see anything that our eyes sees. It's actually pretty far over into the infrared. And there's a reason for that. They wanted to look at the earliest galaxies in the earliest times in the universe. And what I mean by that is they're committed to the Big Bang model, which has been the dominant cosmogony for half century. And currently they think the universe began suddenly 13.8 billion years ago in a very hot, dense state, and it's been expanding and cooling ever since. And they thought that stars and galaxies really couldn't get going until about 1 billion years after the Big Bang. The Hubble Space Telescope began finding galaxies earlier than that at great distance, because according to the light travel you get, if something is, say, 10 billion light years away, then you're looking at it 10 billion years ago, which would be 3.8 billion years after the Big Bang. So they want to get farther and farther out. Now, the light out there...
Without making you go down a rabbit trail, can you explain how they know that they're early? Like, how is that conclusion come to?
Oh, it's based entirely on the distance. Again, if the universe is 13.8 billion years old, then if you see something that's 10 billion light years away, that's how far light would travel in 10 billion years. then it must be, you take 13.8, subtract the 10 billion, and that gives you 3.8 billion after the Big Bang. It's entirely based upon the assumption of how old the universe is, and you think you know the distance properly.
Okay.
And the distance is usually determined from the redshift, which is something that was discovered by Edwin Hubble in 1929. People say he discovered the expansion of the universe. What he really discovered was that there's a correlation between distance and redshift, redshift being how far the spectrum is shifted towards the red end of the spectrum, towards longer wavelengths. It's something like, but not really the same as, a Doppler shift. We use Doppler shift to measure velocities of raindrops in storms, cars that are speeding, all those kind of aircraft, all sorts of things. So it's a pretty well-proven technology. So we measure these redshifts, and what he found was that the greater the distance a galaxy has, the more redshift it has, which is consistent with the universe expanding. So he found the correlation. The interpretation is that the universe is expanding. So the problem is, when you get really far out there, not only are the galaxies very faint because light drops off with increasing distance at a very quick rate, the light that we're most interested in, which is normally in the visible part of the spectrum, is redshifted way over into the infrared. And so if you want to see them in the most interesting part of the spectrum, the part we really want to talk about and study, you have to build an infrared telescope, and you can't do that from the ground because water vapor absorbs virtually all the infrared. So you have to put it up in space, which is why it's in space. It's a very big telescope, much bigger than the Hubble. So there were two primary objectives that the James Webb Telescope was built and designed as built for. And one of them is to determine the very early structure of these galaxies at the first 500 million years or so. And again, remember, the expectation was you weren't supposed to see galaxies, at least not very many of them, in the first 500 million years or even more. And so far, they've not actually measured spectra. They have to look at the colors that they're getting to figure out roughly how far away they are. They're going to come back later and try to get that more accurately. But right now, they're working off the colors. And they're getting now what they're, I wrote an article on this recently on our website at answersingenesis.org about this, and they were arguing that they're now seeing galaxies only 200 million years after the Big Bang. And that's a real problem, because 10 years ago, nobody would have predicted that. They would have said, no, you couldn't have had galaxies that early on. And those galaxies are fully formed. They've got structure. They look very similar to nearby galaxies. There are some systematic differences, slight differences, but not great differences. But they were expecting that first stars would form, and it'd take a while for that to happen. And then stars would kind of amalgamate and form small galaxies, and then small galaxies amalgamate with other galaxies, form bigger galaxies. And so it's a kind of bottom-up hierarchy where you start with stars and work your way to larger and larger structures. And that's been totally ripped up in the last month or two, because what they're finding is that these galaxies seem to be fully formed, and they hope to keep pushing it back farther and farther and farther. So some creationists have been saying that the Big Bang model is disproved, and I guess that's technically true. But what's going to happen is they're going to refigure the Big Bang model.
So they're just going to add more years to it? Is that what,
No, they're just going to change how they think the early universe developed. The Big Bang happens, and then the question now comes, how did stars and galaxies form? And what they do, every time that the Big Bang model runs into problems, that it has over the past half century, they always just change the model around to make it fit what they now observe. And we can come back a little later on what I think that means philosophically, dealing with the philosophy of science. So what people are saying, well, it's the death knell of the Big Bang. Well, I've heard that kind of story before. It's the death knell of this particular version of the Big Bang model. I'm confident that what's going to happen is that they're just going to come up with a different Big Bang model that's consistent with what they're observing. Mm-hmm. And again, I'd like to explore with you in a few moments here the ramifications of that vis-a-vis philosophy of science, because I think that's very important. Another thing that concerns me, and I've been talking about this off and on for years, is the Big Bang says that the universe began with hydrogen and helium, a little bit of lithium, and really nothing else. So the oxygen we breathe, the nitrogen we breathe, the carbon that's basis of all life, the iron in our blood, the calcium in our bones, all of those things, none of them came from the original Big Bang. They were all forged inside of stars. They stars do nucleosynthesis, fusing together smaller nuclei to make bigger nuclei of atoms. So you come with carbon, then you build oxygen, and you build nitrogen, and all those things progressively more and more heavier elements as time goes by. But that takes time. It takes multiple generations of stars to do that. Astronomers call that chemical enrichment. So you would expect that the most distant things you see in the universe should be pretty void of any heavy elements. Well, they have taken some spectra of those distant objects, and they're finding neon and carbon and nitrogen and oxygen. So it's there.
Wow.
And where was the time? It seems like time was really sped up or something, and they're going to have to change that as well. And there's some questions about the earliest stars in general being lacking the heavier elements. They should actually be fainter, but we're finding very bright stars. I think they're just going to argue that the first generations of stars, for whatever reason, were very massive stars, and that's part of the paradigm they're going to go to now. Now, if you ask we creationists, special creationists, what we would expect, and I was talking about this again before the James Webb Space Telescope. I wish I would have talked about it more explicitly now, but we expect it to be galaxies all the way back. The reason for that is that we believe that God made the galaxies on day 4 when he made the astronomical bodies. At the end of day 4, it says that God saw that it was good. And at the end of day 6, it says God proclaimed over the entire creation it was very good. And that goodness gets across the idea of completeness, that what God had created is now fully functioning. At the very beginning of the creation week, and in verse 2 of Genesis 1, it says that what was there was unfilled and unformed. It says, it wasn't say in the King James, void without and empty, without form and empty.
Without
That's what
form
it's
and void. Yeah.
void and without form. And I think it's better getting across by being unfilled and unformed. But then the end of the creation week, it's formed and it's filled. God spent all 6 days shaping and forming that initial creation to get what it is at the end of the creation week. And so we're not going to be seeing a bunch of evolution of galaxies and stars as we go to great distances. We are going to see galaxies because that's the way God made it. Unless at great distance we get a peek at what was going on during creation week. I don't think that will happen, but there are some people who suggest that could happen. So that's our expectation. And what we're finding is the data so far, the observations so far are consistent with what we creationists expected all along. So we're very happy. We're very excited about what we're seeing because it's exactly what we predicted would happen.
Yeah. Well, that's great. One of the things that really stood out to me about the article that I read, and again, I couldn't really fully understand the whole thing, but one of the conclusions that the gentleman came to was that it appears that the cosmos started off in an almost pristine condition and then faded with time, rather than starting off with nothing and then slowly evolved over time.
Yep.
And yep. I think would that be a fair conclusion to come to from what we're seeing from the James Webb?
I think so. Yeah, that'd be a very fair layman summation of what he said. Yeah.
And that's very consistent, of course, with creation. Yeah. It seems like what we're finding is going to have to make evolutionists and even theistic evolutionists have to redo their models, but it doesn't seem to change a young Earth creationist model, does it?
No, we have changed our models from time to time, but this one isn't at this point not cause us to change. Yeah. And you mentioned the change in the models, and I alluded to that. I want to get back to that. Yeah. There was a guy named Claudius Ptolemy in the early 2nd century AD put together this theory of motion of the planets and the sun and the moon. The stars remain relatively fixed. They don't change their positions relative to one another. The stars change throughout the night that you see, and also the stars change from season to season, but they come back tomorrow night, they come back next year. So the constellations we look at are pretty much what people saw thousands of years ago. Job mentions Orion. I look at Orion, I'm seeing the same thing he saw. But then you get 7 objects that move with respect to the stars. The moon takes once a month to go through the stars. The sun takes, that's due to its orbit around the Earth, of course, and the sun takes a year to go through the stars, and that's due to our orbit around the sun. And then you get the 5 naked eye planets. They look like bright stars. They're Mercury, Venus, Mars, Jupiter, and Saturn. They go traveling along and they change direction and move back and forth, it's because of their motion around the sun, and our motion around the sun gets combined with this back and forth motion. And it defied explanation until a guy named Ptolemy, as I mentioned, came up with this model where you have the planets moving in a circle like this, with the Earth kind of near the center, but then that circle, actually the planet's moving on a small circle, and then it's on a larger circle that moves around the Earth roughly. So you get this very complicated spiraling motion that takes place. And it turns out it worked pretty well to describe motion. It became very popular and was dogma for 15 centuries. The strength of the Ptolemaic model was that whenever there was a discrepancy between observations and the theory, you could always add more little epicycles, little tiny circles. So by the time you get to around 1600, you went from about a dozen epicycles to well over 100 epicycles just to make it fit. So I would tell people, my students, and I used to teach and anybody listen to me when I talk about it, the strength of the Ptolemaic models, it could be indefinitely improved upon with more adjustments being made to fit the data. But the downfall or the shortcoming or the failure of the Ptolemaic model was that it could be continually modified to fit new data, because after a while it became a very complicated model, and people applied what's called Occam's razor. The idea, the simplest explanation is probably the correct one, and people looked at that and realized this is crazy. This model has just gotten too complicated. Ultimately, you can't falsify that model either. In science, we're always talking about disproving ideas. If you can't disprove an idea, then it gives you confidence it's probably true. It's kind of a backward way of looking at it, but that's the way science works, because we're working with inductive reasoning for the most part, and you don't prove things like you do in mathematics or deductive reasoning. So we try our best to disprove ideas, and if we can't disprove them, then we have confidence they're probably true. So science changes over the years, and when you come to the Ptolemaic model, it could not be falsified, it could not be disproved. So it really wasn't a good theory. A theory explains anything and everything really isn't a good theory at all in science.
Yeah.
And I fear that the Big Bang model has become that, because the Big Bang model's been around not quite as long as I have. I was in school growing up when it became widely accepted, so most of my life, most of my experience has been based on the Big Bang model, but it's changed remarkably over the years. The expansion rate has changed, and hence the age of the universe. It used to be 18 to 20 billion years. Now it's 13.8 billion years, plus or minus 1%. Let's see, they've added dark matter and dark energy. Those weren't really considered 30 years ago. They've added string theory. They've added all sorts of other things, and they just changed things around. I remember back a little over 30 years ago, the Kobe experiment was looking at the cosmic microwave background. That's a relic, microwave radiation coming from every direction in space from a period of a few 100,000 years after the Big Bang, supposedly. And it's they were looking for temperature fluctuations that were necessary to explain galactic structure, how galaxies formed in the first place. It'd be a little warmer and cooler areas, and printed upon that. And they predicted variations of 1 part in 10,000 in the temperature. The temperature around 3 Kelvin, which is really, really cold. And what they found was the prediction was off by a factor of 10. It's 1 part in 100,000, not 1 part in 10,000.
Wow.
So what did they do? Well, they just went back and they redid the theory to match the data, and then they claimed that the predictions beautifully matched the theory, matched the observations. I say, wait a minute, that's not true. But you found out the model didn't work. The theory was wrong by a factor of 10, and so you just redid the theory. But don't tell me that the theory predicted it didn't. The theory predicted it after the fact, but that's just fitting it to the data. And I think the same thing is going to happen here. They're going to say, oops, our model was disproved, but let's just change the model a bit to make it fit. And that's what they're going to end up doing. And they've done it repeatedly over the last 50 years. And so it's starting to me, the Big Bang model is resembling the Ptolemaic model. You just keep changing it to make it fit. As I said before, a theory that explains anything and everything doesn't explain anything, because it can't be disproved. And I think it's not even really qualifying as a scientific model then anymore.
Yeah, if every time something's disproved, you just change it and it's not disproved anymore, you're right. It's not falsifiable. It can't be a viable a viable theory. That really applies to more than science. I mean, that applies to a lot of different areas of debate and other sort of logic. But now let's take, if we can, let's take the data that we're seeing and let's see how it fits with the young Earth creationist model. Because I know a lot of people, this is one thing that a lot of people came to me and said, hey, look, we're seeing back billions of years into the past, which means that the universe has to be billions of years old. And honestly, I tried to answer that, being a young Earth creationist myself, but that's something I feel like I want to pass on to you. How do you answer that? Does this mean that the universe is billions of years old, since, light has to travel billions of years to get here from these stars?
Well, I'll admit that that's the most straightforward interpretation of the data. I mean, if I were going to make an argument for billions of years, I would go there every time. However, I believe Scripture makes it very clear the universe is quite young. I don't know exactly how young, but I think on the order of a little over 6,000 years. We call this the light travel time problem. We look out and we can see. I can see with my naked eye on a dark, clear night this time of year, the Andromeda Galaxy, and it's about 2.5 million light years away from us. And so we will ask, how can you see such a distant object if the world is only thousands of years old? We don't worry about stars nearby because that's not really a problem, you see, because we don't really see any stars that are farther away than 6,000 light years anyway. But you know what? We kind of shortchange Adam, because Adam had a light travel time problem. He when he looked up on the end of day 6, and the night fell, beginning of day 7, and first time he looked up in the night sky, what did he see? Well, I think he saw stars. Yeah. Even though the stars were only made on day 4, that's only 2 days earlier, and the nearest star outside the sun is more than 4 light years away. I don't think, he waited 4 years and 4 months, and then bink, there's one star, and waited another 10 years, there's another star. I think he saw pretty much what we see. And the reason why I say that is because the stars were given certain functions and purposes on day 4 when God made them. And remember that goodness I talked about. The goodness talks about completeness and fulfillment. They were fulfilling their functions that they had, and they could not fulfill those functions if they were not visible. So Adam had a light travel time problem, didn't he? We obsess over the most distant things in the universe, but actually he had a difficult time seeing nearby things, not things in a solar system, but things a few light years away from us. How did he do that? I think if we can solve his little problem, we can probably solve our little problem too. And I note 2 things about the creation week. Many times we think everything in the creation week was ex nihilo, that is, made out of nothing. Initially, the creation was done that way, and several things during the creation week were done that way, but most of the things were not. God made man out of the dust of the ground. Later on, we see he made the land animals and the birds out of the dust of the ground. He caused the plants to grow out of the ground on day 3. They just didn't poof appear like that. And furthermore, we also sometimes assume that it's all instantaneous. Poof, the whale appears. Poof, this tree appears. And that's not what it says. He used a lot of process. Even the making of Adam was a process coming out of the ground. It took a little bit of time. So I see a lot of process taking place. And it's working towards that fulfillment. The plants had to grow up and become mature very rapidly, because we know from the end of the chapter, the man and every beast ate vegetable matter. They didn't eat meat. And so they had to be able to eat the fruit of those plants, and they had to be mature in order to do that. You couldn't do it any other way. So I think in similar manner on day 4, God rapidly matured that light, as it were. He brought the light to the earth. So when I look at the Andromeda Galaxy, I believe it's over 2 million light years away, but I don't think that light's been traveling nearly that long. I think it's been traveling something closer to 6,000 years. It's a miracle. Many of my physics and astronomy colleagues in the creation movement, they want to invoke a physical explanation based on general relativity or something. I think that's wrong. I think we should be doing it, realizing that everything else in the creation week was miraculous. Why would that not be miraculous too?
Interesting. So it's about maturity. If God can rapidly mature living animals and living beings and living plants, he can also rapidly mature a light traveling from a star.
And it's a little different from mature creation. Henry Morris was very fond of what we call mature creation, or creation of light in transit. He said he just created them mature. And I said, no, he matured them rapidly. He went through a process to rapidly mature them. So it's a little different explanation from his. But I think that's how this is done. I might want to add to you here that the Big Bang model has a light travel problem too. A lot of people don't know that. It's called the horizon problem. I remember I mentioned the cosmic microwave background. It's called CMB for short. It's about a three Kelvin microwave background coming from every direction in space. It was discovered in the mid 1960s and was taken as the first evidence and the big proof of the Big Bang. And what it means is you're looking off in this direction, and you will see a radiation field with a little under 3 Kelvin temperature, like 2.73 something 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 temperature. We can measure it to like 5 significant figures, or even better than probably at least 5 now. And then you look off in this direction, diametrically opposite, and you see exactly the same temperature. And it doesn't matter which direction you go, this way and that way, this way and that way, you see precisely the same temperature in diametrically opposite things. Now, it's a principle in physics that two things will come into what we call thermal equilibrium, or if you will, the same temperature, only if they've had the opportunity to exchange heat through conduction, convection, or in this case, radiation. But if we're sitting here and we're receiving radiation from 13.8 billion light years coming this way from point A, and we're receiving radiation from point B, 13.8 billion light years away, radiation from point A has never reached point B, and radiation from point B has never reached point A, has it? It's just getting to where we are in the midpoint. So why are they the same temperature? It's a mystery why the universe has the same temperature throughout. And they realized this problem in the 1970s. It was about 40 years ago in the 1980s that Alan Guth first proposed what we call cosmic inflation, the idea when the Big Bang happens, it's rapidly expanding, but then about 10 to the minus 34 seconds or so after the Big Bang. Think about that, 10 to the minus 34 seconds. It's point followed by 33 zeros and a 1. The universe starts expanding at many orders of magnitude faster than the speed of light. The universe expands really, really fast, far faster than light. And then about 10 to the minus 32 seconds, it abruptly stops doing that and goes back to normal expansion. And the idea is before this hyper expansion took place, the universe came into thermal equilibrium. That is the same temperature. And then when it hyperinflated like this, it took the universe out of thermal contact with much of itself. And it's only slowly redeveloping that. So they had a light travel time problem. How did the light from over here get over there? And they solve it by invoking cosmic inflation. Now, it's been around for 40 years. Do you know how much evidence there is of cosmic inflation?
None.
None.
I'm guessing.
That's exactly right. And to me, I mean, if you have no evidence for a past process, then it suggests that, well, maybe it was a miracle. I mean, they get on our case because they say, well, you're just invoking a miracle. Well, so are you. Give me a physical explanation, some evidence that this actually happened, and they can produce neither. So consequently, they're invoking a miracle, so they choose not to call it a miracle. I'm not ashamed to call it a miracle because it's consistent with what I'm doing. They can't invoke a miracle because, well, they're committed to naturalism, so they have to make up this cockeyed idea about it. So make no mistake about it, the Big Bang people, they have a light travel time problem too.
Yeah, this has all been so educational and so helpful. Dr. Faulkner, thank you so much for coming on and explaining this. And I probably will have, after I think through this whole topic, like a whole list of more questions to ask you the next time we have you on, because we'll have to have you back sometime. Thank you so much for your expertise.
It's been so much fun. I'd love to do it again.